Welcome back to another video where today we're going to be determining the temperature of an adiabatic flame. So think like your Bunsen burner or your plant flare, okay? And we have some conditions and considerations to go over. First and foremost being that this reaction is happening at steady state. In other words, the change in heat is actually going to be zero, okay? Therefore, we can say that the enthalpy of reactants going out the enthalpy of reactants going in is equal to the enthalpy of reactants going out. Okay? And I'm just rewriting this expression here and expressing enthalpy as enthalpy multiplied by small change in mass. Okay? This expression is held to be true. And the second thing to consider is we don't have a pure fuel. Instead, we have a fuel mixture dictated by these mole percentages. We also have 20% excess air in these conditions, and assuming the normal, mole percent of air, nitrogen and oxygen. Okay? So, what's going to happen is this combustion is going to follow the combustion reaction, right? Methane plus oxygen plus nitrogen is not part of the reaction. However, it's important to consider it as it does carry some enthalpy. Okay? So that's why we're going to consider it here. Equals CO2, carbon dioxide, plus water, again, plus nitrogen. Okay? Let's balance this equation. We have four hydrogens, and 2 over here. So we need a 2 in front of the water. We have 1 carbon and 1 carbon, so that's good. We have 2 oxygens plus 2 oxygens. We have 4 oxygens over here and only 2 over here. Therefore, we need a 2 here. Now, we need to consider the mole percentage of nitrogen to oxygen, because in air, nitrogen exists in a 79 to 21 mole ratio, right? As well as for this, we need to consider the stoichiometric coefficient of oxygen as well. And since nitrogen is a non-participant in the reaction, the coefficient between in and out is actually the same. Okay, next let's consider ethane. Okay, same song, right? We have oxygen and nitrogen, and that says some carbon dioxide and some water and nitrogen. Okay, let's balance this. We have 2 carbon over here and only 1 over here. Therefore, there needs to be a 2 out there. We have 6 hydrogen and only 2. Therefore, we need 3 out here. Let's count our oxygens now. We have 4 plus 3, 7. Okay? Therefore, a 7 over 2 must go in front of the oxygen. Okay? Are we done here? Not yet. Don't forget that the stoichiometric coefficient of oxygen must also go in front of nitrogen, because it is coming in as air. It's coming in as a unit, okay? And we now have 2 derived expressions for a reaction for which this problem will follow. And you might be thinking, hold on, you forgot to do propane. Well, we don't actually need to write an expression for propane because we're going to do some fancy matrix math in order to account for the fact that, hey, the reaction is not proceeding for a 1-to-1 ratio of methane, ethane, and propane. Instead, it's this ratio right here. Okay? And all we need is to see the relationship between these two, to see what the relationship between each reactant and product is, to write an overall balanced equation for the combustion, okay? We'll do that later. We'll do that in Python, okay? The last thing we'll need to consider is that enthalpy, H, is equal to the partial derivative of enthalpy with respect to temperature given constant pressure, dt, plus the partial derivative of enthalpy with respect to pressure given constant temperature, dp. Okay? And we can further simplify this expression because we know that this reaction is happening at an assumed ideal gas. Therefore, this term actually cancels out. Well, not cancels out. It's equal to 0. Okay? Therefore, this is our term for enthalpy. Okay? We'll meet you in Python, where we're going to continue solving for this temperature of an adiabatic flame. Okay? Okay, we're back in the computer, and you see a couple of equations in front of you, and let's walk through them. The first one is the final equation we had derived on the iPad, and I forgot to mention one very important thing about it. That being that this expression is so common that chemical engineers have decided to give it a name, CP, or in other words, the specific heat held at a constant pressure, right? That's basically what all this is. But there is one thing to note, and it's that this expression is only true for small changes in temperature. Well, we don't have a small change in temperature. We're combusting something, and something gets very, very hot, okay? Why does that matter? Because at larger temperature changes, the specific heat C actually changes, okay? So what can we do? Well, let's pull upon equation 103 from ChemCAD. And what is it? Well, it's a function with independent variable temperature and some arbitrary constants based on what component you're looking at, and it spits out a dependent variable, that being specific heat, okay? Now, why does this matter? Well, if you look at this expression, if we integrate it, well, we no longer have a small change in temperature T. If we integrate it, we can now say that enthalpy is equal to specific heat held at constant temperature. So we take this expression and then we integrate it, and we integrate it by Wolfram Alpha or Symbol Lab, whatever calculator you prefer, because if I'm being totally honest, I do not want to integrate this by hand. Okay, but otherwise we get this expression. Okay, so let's hop into Python, where we have our standard imports. Okay, we have the CHE tools package, because we do need that, and we defined an object P, which contains the properties of all of the interested components for this combustion reaction. Okay, first thing we want to do is let's define a function called int CP, okay, or integral of specific heat, and this function is taking in an independent variable temperature, and what it's returning is this expression right here. Okay, so we return p dot. Okay, let's explain this really quick. P dot CP IG. Okay, what that stands for is P, the properties of our components for specific heat of an ideal gas, and ABCDEFG, that is our arbitrary constants. Okay, so that times temperature plus P dot CP constant B times constant C, okay, all over hyperbolic tangent constant C over temperature. Okay, minus constant E times constant D times hyperbolic tangent constant E over temperature. Okay, there's one more thing to note, and it's that this equation, it actually gives us units of kilomoles. Okay, sorry, kilojoules per kmol. Was that it? No, it's kilomoles. Okay, so what we want to do to account for that, because we want all of our units to line up, we divide everything by 1000. Okay, and you'll see why in just a second. We want to define a second. We'll want to define a second function. We'll call this enthalpy. Okay, taking an independent temperature G, an independent variable T, temperature, and what it's going to return is the difference between, let's see, P dot H, heat of formation of an ideal gas, plus our enthalpy at a certain temperature, so int Cp, because this expression is equal to enthalpy at a certain temperature, minus our beginning, which is at room temperature, right? Our initial conditions, room temperature. Okay? What we're going to use these functions later on in order to use scipy.root to find a temperature T to minimize this difference. Remember, because of our steady state, we say that the enthalpy of enthalpy of components going in is equal to enthalpy of components going out. So we're going to use scipy.root there. What we're going to do now is use some matrix multiplication to derive some stoichiometric coefficients for our overall combustion reaction, including the entire fuel mixture, right? So let's start with that, the fuel mixture. So fuel mixture, and we're going to make this an array. And it's 95, sorry, is it 95? Yeah, it is. 95% methane, 4% ethane, and 1% propane, right? Next, we're going to define our atom ratios of each component, okay? Starting with methane, which has one carbon, 4 hydrogen, right? Ethane has 2 carbon, 6 hydrogen, right? And propane has 3 carbon, 8 hydrogen, okay? And very simply, the stoichiometric coefficients of carbon and hydrogen is the matrix multiplication of fuel mixture and atom ratios, okay? And let's check that while we're at it. And it's 1.6 carbon and 4.12 hydrogen, which makes sense because our mixture is mostly methane with some other things mixed into it. So it should be something close to methane. Okay? Now from methane, we can from our stoichiometric coefficients of carbon and hydrogen, we can derive the rest of the coefficients of the rest of our components. Starting most simply with carbon dioxide. What do you notice? For every carbon there is 1 carbon dioxide. Every 2 carbon, there is 2 carbon dioxide. So the coefficient of carbon dioxide is very simply the coefficient of carbon. Next, most simple, is that of water, because for every molecule of water, there's twice as many molecules of hydrogen in the fuel. Okay, so therefore the coefficient, what just happened? The coefficient of water is the coefficient of hydrogen in the fuel divided by 2. Next up is oxygen. The pattern is there, but it's not so easy to notice. It is very simply, the coefficient of oxygen is very simply the coefficient of carbon dioxide plus half that of water. 1 plus 1 equals 2. 2 plus 1.5 equals 3.5, or 7/2. So, n, the coefficient of carbon dioxide plus the coefficient of water divided by 2. And we need to account for excess air as it was part of the problem statement, right? So excess air is equal to 20. We multiply this by 1 plus excess air, 1.20, right? And finally, the coefficient of nitrogen is very simply the mole ratio, 79 to 21, multiplied by that of oxygen. Okay? Very simple, right? Next, we want to make an array of our components going in and our components going out. Okay? We're going to want to concatenate two arrays, starting with our fuel mixture, right? Fuel mixture. And I believe this wants it in an array, so np.array. Okay? Our fuel mixture, because methane, ethane, propane. What's next? It's going to be oxygen. Well, oxygen at the beginning, NO2. Okay? Nitrogen, N2. And we don't have any carbon dioxide, nor do we have any water at the beginning. So, 0, 0. Okay? What's next? We have things going out. We no longer have any fuels. So it's all 0. I just had a big voice crack there. All 0. And because of the excess air, there's going to be some oxygen left, right? So what's that? It's going to be the percent excess multiplied by the coefficient of oxygen. Very simple. Well, what's next? Nitrogen does not react. It's always present. Carbon dioxide. Ooh, wrong hotkey. And water. Okay. All good. Ooh. Do I have one too many? What is that like? Concatenate. Invalid syntax. Oh, I'm missing a square bracket. There we go. Oops. Okay. Well, let's finally get to the culmination of all of this. Let's set up a function for which we're going to use root on. Okay? And it's going to be unpack our vector of unknowns. And we're going to return, recall that it's going to be the difference of enthalpy of our products going out minus the enthalpy of things going in. Okay? And for our steady state system, that should be as close to 0 as possible. It should be 0, but root is going to get that as close to 0 as possible. So it's going to be the dot product of two vectors. Those two vectors being the enthalpy of reactants at temperature T, which we do not know, and our components going out, minus np.dot the enthalpy of our reactants at 298 Kelvin room temperature, and our components going in, right? Okay, let's try root now. Root. We want to use the root on temp, and we want to have a guess, I don't know, about 2000. Okay, and there we have it. The solution has converged, and we have our adiabatic flame temperature of 2063 degrees Kelvin. Very hot, right? And with that out of the way, this concludes homework 5, and I will see you next video.